Okay. So good afternoon, brother. So sorry for the delay because I have some issue on my writing board. I think now it's working. Understand? Do you hear my voice?
Yes,
Yes,
Doctor.
doctor.
Okay. So the title of today's lecture is Entropy and the Second Law of Thermodynamics. My dear, could you please recall what we studied in chapter number 18? In chapter number 18, we studied the laws of thermodynamics. Am I right? How many laws we have in thermodynamics?
3.
4.
Four
Four,
laws.
Doctor.
Am I right? Zeroth law of thermodynamics, first law of thermodynamics, second law of thermodynamics, and third law of thermodynamics. Am I right?
Yes, you are right.
So today we are going to discuss only the second law of thermodynamics based on the new terminology entropy. Actually, entropy is the terminology we have to use in the thermodynamics for indicating some important things. So please, my dear, listen the class carefully, and we are going to study only few topics from this chapter and only 3 formulas. And based on these 3 formulas, you are going to solve 5 questions. Very easiest chapter, and problem wise, it will be very easiest one. And please listen the class carefully. So what are the topics today we are going to discuss? We are going to discuss the definition for the second law of thermodynamics, and then we are going to study the concept of entropy, and then we are going to study 2 cases. What is the entropy in the real world based on the engines and refrigerators? That means everything is in our day-to-day applications. The applications what we are going to use in our day-to-day life, and that information we are going to study today. Understand? Clear, my dear?
Yes.
Okay.
Yes.
Let's start with the second law of thermodynamics. Could you please tell me what is the definition for the second law of thermodynamics?
Heat transfers from the hotter
Very
region
good.
to
So
the
heat
colder one.
will always moving from hot region to the cold region. Am I right? This is a standard definition for the second law of thermodynamics. But today we have 2 more extra definition for the second law of thermodynamics. What are the 2 more extra information? So listen carefully. In this slide, I am giving the picture of the heat engine, because if you want to work this heat engine, you need some energy. That energy you have to take from the hot reservoir. So if you want to run this engine, you have to take this energy, and also you have to perform some work based on the energy what you take from the hot reservoir. Clear? While you do some work, what will happen? Some energy will be going to the cold reservoir. Am I right? Am I right or not?
Yes, you are right.
So if you want to run this heat engine, you have to do some work done. And what is that work done? This work done is exactly based on the energy what you are going to take from the hot reservoir. So in our day-to-day life application, the heat engine picture, if you just see this picture, without this part, it is not possible. For example, you are going to take 10 joules of energy from the hot reservoir, and you are going to do some work based on the energy you are going to get from this 10 joules. How much of work you are did? You are just doing the work of 6 joules. What about the remaining 4 joules?
It's gone to the cold.
It will be going to the environment. Am I right or not? For example, my dear, you can take an example of your car. If you want to run the car, you need the fuel. Am I right?
Yes, you are right.
Did you use the entire fuel for running the car? Is it possible?
No, we lose some.
So some amount of the energy will be wasted. Am I right or not? It is going to the environment. Am I right?
Yes, you are right.
So the same thing happened here. So if you want to do some work of 6 joules, you have to take 10 joules of energy from this hot reservoir, and this 4 joules of energy will be getting wasted. So what is the formula for work done? The formula for the work done is nothing but energy from the hot reservoir minus energy from the cold reservoir gives you the answer for this work done. Am I right? How much energy you are taking from the hot reservoir? 10 joules. Am I right? How much of energy is going to the environment? 4 joules. What is remaining?
6 June.
6 joules. So in our day-to-day life, is it possible to have the picture like this without losing any energy? Is it possible?
No, Doctor.
No.
It's
So
not
in
possible.
our real world, so without losing some energy, it is not possible, because without losing the energy, if you want to run any work, it is not possible in our real world. So if you just see these three pictures, this picture is maybe applicable for the ideal world, but this picture is exactly applicable for the real world. Clear? Understand?
Yes.
Yes.
It's,
Okay,
Yes,
what is the
doctor.
definition? Could you please read? So what you understand from this? There will be no 100% efficiency of the engine. Is it possible to get 100% efficiency?
No.
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 Not
For example,
possible.
you are having an engine. Is this for example, you are designing one engine. That engine is giving 100% efficiency. It is possible. Is it possible in the real world?
No.
No.
Doctor,
So in our real
also
world,
the bond.
this no 100% efficiency will never happen. So that is an definition for the second law of thermodynamics. So what you understand from this slide, it is impossible to extract all the energy from the hot reservoir to do the work. So if you want to do some work, some of the energy must be lost. Am I right?
Doctor, also
Yes.
with bomb,
Also about the
with bomb.
yes, of course, your phone. For example, you are charging the phone 100%. Is it possible to use this 100% perfectly without losing any energy?
No, it's not possible.
Because every time
Just,
you are charging your phone, am I right?
yeah.
So some energy loss is there. Am I right or not?
Yes, you're right.
You can just charge your phone. You can travel from Jubail to Dammam. After that, you can just see your battery. Your battery will be a little bit discharged.
Of course.
Am I right? So it is
Yes,
not possible
you're
in the real world. No 100% efficiency of the engine is not possible in this real world. So there may be some loss of energy. So if you want to write the definition for the second law of thermodynamics, you have to say it is impossible to extract all the energy from the hot reservoir to do the work. So if you want to run the engine, you have to do some work with loss of some energy. Clear? Clear?
okay, clear. Doctor, what's the difference between transfer the energy from hot to cold and the definition, what you said about second law of thermodynamics?
You can see the slide. You can see the slide. I already moved the slides. So that definition is here. You can just have a look here.
It's
So what is the
possible for
general
me.
definition for the second law of thermodynamics? The heat will always flow from hot region to the cold region. Am I right?
Yes, called
For example, you can take an example of the refrigerator or air conditioner in your home. What is the purpose of this air conditioner, my dear? What you are exactly doing with the help of this air conditioner? Could you please tell me?
it is transfer from the hot.
It will remove the hot energy. It will remove the hot temperature from the room, and it will make the room too cold. Am I right?
Yes, you're right.
So here the work is doing in the reverse order. Am I right or not?
Yes.
So here the heat is transferred from cold to hot. Am I right?
Yes, you're right.
So, but in our real world, if you want to do the heat transfer, always the heat will be transferred from hot region to the cold region. But if you want to do the reverse work, what you have to do? What is
we
W?
added more energy.
My dear, listen. First of all, listen. For example, if you want to remove the hot temperature from the cold, you want to make the room cold. Am I right? Generally, the definition for the second law of thermodynamics, the heat always transfer from hot region to the cold region. Am I right?
Yes, you're right.
Now you want to remove the hot energy, hot temperature from the room, and you want to make the room too cold. So you are doing the reverse process. Am I right?
Yes, you're right.
So if you want to do the reverse process, what you have to do? You have to do some work. Am I right?
Yes, you're right.
For example, you can see here, I want to make the room cold. So what I have to do? I have to do some work. So by that, my cold energy is going here. My hot energy is going outside. Am I right?
Yes, you're right.
So it is a reverse diagram of the engine. You can see, you can compare this picture and this picture. It is totally opposite to each other. Am I right?
Yes, you're right.
You can see the arrow mark. Here the arrow mark is coming here. Here the work done is going to the right hand side. Here the cold energy is going to the downward direction. But if you just see this picture, what you understand, your work done is the inward direction. Your QC will be in the upward direction and your QH is in the upward direction. Am I right?
Yes, you're right.
So, my dear, in your home, you can just see your refrigerator. If you want to make your refrigerator more colder, backside of this refrigerator, you have the component called compressor. Am I right?
Yes, you're right.
Without compressor, is it possible to run the air conditioner and the refrigerator?
No, doctor. It's not
So, what is the function of the compressor?
Does the work.
The compressor is doing the work to remove the hot temperature from the room to outside. Am I right?
Yes, you're right.
It will remove the hot temperature from the room and it will make the room colder. So what you understand from this slide, it is impossible to transfer the heat from the cold to hot. So if you want to transfer the heat from cold to hot, what you have to do?
I did work.
You have to do work. For example, you can see the picture. Is it possible to remove the hot to cold by this picture?
No.
So without work, is it possible to move the hot to cold? It's
No,
not possible.
doctor.
So what you have to do without doing this work, so the compressor is doing these things. With the help of the compressor only, we are removing the hot temperature from the room and we make the room colder. Clear?
Clear.
Yes.
Okay, very good. Let's come for the third definition, the third different temperature. My dear, listen carefully. Actually, the definition for second law of thermodynamics, you have three statements. What is our first statement? No 100% efficiency. So if you want to design any engine if you design and that engine will never give 100% efficiency. Clear?
Clear.
The second
Yes.
thing, if you want to remove the cold, if you want to remove the hot temperature from the room, what you have to do? You have to do some work. Without work, you would never transfer the heat from hot to the cold or cold to the heat. So you have to do some work. So here we want to remove the hot temperature from the room. We have to make our room colder. So what you have to do? You have to do some work. So without work, it is impossible to transfer the heat from cold to hot. So unless otherwise, if you are doing some work, if you do work, you can do the reverse process. But if without doing work, what will happen? You would never transfer the heat from cold to hot. Clear? Now we are going to study the third different definition for the second law of thermodynamics. This is the third different definition. What is that? Could you please read here? What is given here?
It is
My dear, read the
impossible.
statement. It is impossible in the thermodynamic process for the entropy to decrease. That means what you understand from this definition, your entropy of the system will never decrease. It will always increase. The entropy of the system is always increase. The entropy of the system will never decrease. My dear, the entropy of the system will always increase for the irreversible process, and the entropy of the system is constant for the reversible process. So keep these 2 points in your mind. So first of all, we must know what is the definition for this entropy. What is the definition for the entropy? Could you please read this line? What is the definition for the entropy? What do you understand from this line?
A measure of amount of energy that is unavailable for work.
What do you understand?
Like,
just tell me the
losing some energy.
Okay. For example, my dear, listen carefully. I have a heat engine picture here. Am I right? You can take an example of the car.
Yes.
So you run the car. So if you want to run the car, you have to extract the energy from the hot reservoir, and with that energy, you are doing some work. Am I right?
Yes, you're right.
Yes.
And some of the energy will be losing. Am I right? It's going to the cold reservoir. Am I right?
Yes.
Yes, you're right.
For example, take an example of the car. You are starting the car and the car is running, and at the same time at the back side of the car you have the silencer. Am I right?
Yes,
Yes.
you're right.
From the silencer, what you will observe? The smoke is coming outside. Am I right or not?
Yes.
Yes.
Is it possible to use that smoke for doing some work?
No.
Yeah.
Who said yes? Is it possible to use that smoke that which is coming outside the car? Is it possible to do some work by using that energy?
No.
No.
So that information is given here. It is a measure of amount of energy that is unavailable for the work. By using that smoke, you cannot be able to use that energy for doing some work. Understand?
Yes, doctor.
Clear? And always your entropy of the system is greater. It has the greater value. It will never decrease. Your entropy of the system is always increased, or sometimes it may be constant. So when it will be increased, if the system has the irreversible process, then the entropy of the system is always increased. Suppose if the system has the reversible reaction, the entropy of the system is constant. So your entropy of the system will never go negative value. It will be always positive value. It will be always have the increasing value of entropy, and sometimes it may be constant. Your entropy of the system will never go decrease. Clear? Understand, my dear?
Can you repeat, doctor, please?
Okay, my dear, for example, take an example of the car. You run the car, you take the petrol for running the car, am I right? And at the same time, backside of the car, you have the silencer, smoke is coming outside, am I right?
Yes.
Yes.
And you cannot be able to use that smoke for doing any work. Is it possible to do any work by using the smoke?
No.
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 That means your smoke is also an energy, am I right? It's a form of some energy. So by that you cannot be able to do any work. So that is the definition for the entropy. And also you have another definition for the entropy. It is a measure of disorder. What is the meaning for disorder?
Terrible.
You can see the picture, and here the bricks are arranged perfectly, am I right? It is in the ordered form, am I right?
Yes, you're right.
And what happened here? Is it in the order or disorder form?
Disorder.
So my dear, if you want to go back to this ordered condition without work, is it possible?
No.
Without rock.
So your entropy of the
no.
without doing work, what happened? You cannot be able to bring back to the order condition, and so your whenever the order is disorder, then your entropy of the system is greater. Clear?
Clear.
Okay, I can give one more easiest example. I think some students, you are staying in the bachelor's apartment, am I right?
Yes.
Yes.
Okay, what is the condition of your room? Is it ordered form or disorder form? If you are living in the bachelor's room, what is your condition of your room? Is it order or disorder?
Order.
Order.
Ah, my dear, generally I'm talking about generally. Maybe one or two you can make your room order, but generally,
Disorder.
how you will maintain your room, my dear? If the bachelor is living in the room, we can easily identify it. The room is not in the ordered form, am I right?
Yes. You're
So the entropy of the room is increasing, greater value, am I right? So whenever you find the disorder condition, you have to say the entropy of the system is greater. Clear?
clear.
Okay, see the third picture. Here I have the ice cube and then water. So after you place the ice cube, what happened? It will be converted to water, am I right?
Yes.
Is it possible to get back this water to solid form
Yes, by freezing.
without any work? Without any work.
No.
Is it possible?
Impossible.
No.
So what you understand from this? Your entropy of the system is greater, am I right?
Yes.
That means this is a reversible process. So if you have the reversible process, the entropy of the system is constant. Suppose if you have the reaction irreversible, for example, you can take an example of the egg. You drop the egg. What will happen to the egg?
Will work.
It will break. Am I right?
Yes.
Is it possible to retain that egg to the original form?
No.
No.
So that means it is an irreversible process. Am I right?
Yes.
So what is your entropy of the egg? Is it greater or constant?
Great. No.
Greater.
Irreversible entropy of the system is greater. Clear? Clear? Keep these 2 points in your mind. Understand, my dear? Clear?
Yes.
Yes.
Okay. Now, this is the definition. So, what you understand from this slide, it is impossible in a thermodynamic process the entropy to decrease. Your entropy is always increasing and constant. Is there any information about the decreasing value? So, your entropy of the system will never decrease. That information is given in this picture. You can see this picture. I have 2 compartments. One compartment is filled with a gas and another compartment is empty. So, now I just make some stopcock in between these 2 compartments, and after some times I am going to remove this cork. What will happen, my dear? This gas molecule will enter this room. Am I right?
Yes.
Yes.
Is it possible to move these gas molecules again back to this room?
No.
No.
Without work.
So
No.
if it is irreversible process, what is your entropy of the system?
Greater than
Greater.
0.
Greater. Suppose if it is a reversible process, what is your entropy?
0. Constant.
It's a constant. 0 means it's a constant. Clear?
Yes.
When
Okay.
doctor come 0 entropy?
When the system, when the reaction is reversible,
Okay.
when the reaction is reversible, this condition. When the reaction is irreversible, this condition. Clear?
Clear.
Can you give
But
us
your
an example?
change in entropy never decrease. Keep this point in your mind. Understand?
Yes.
Okay. Now
Victor, can
we are
you
going to
give us example for the second one?
which one? Which one?
When it's will be constant.
For example, you can take an example of the ice cube and water. You can take an example of ice cube and water.
Yes.
You can convert, because this is a reversible process. Am I right?
Yes.
So if this is a reversible process, your delta is exactly equal to 0. Am I right? Am I right
Yes,
or not?
because I cannot change it.
Yeah, you can convert this water form to solid form again.
Yes.
So if you take an egg, is it possible to return back to its original form if it broke?
No.
No.
So that is the irreversible process. This is the condition. So generally, if you have the second law of thermodynamics, you have to write this statement. So this is the statement for, this is a statement for
Second law.
second law of thermodynamics based on
Entropy.
based on entropy. My dear, listen, my dear. First of all, if I ask you the question, please open your mouth and give me the answer. We can't see each other. We can hear only. If I ask you a question, even though if your answer is wrong, please don't worry. Please give the response. I'm just waiting for your answer. Clear?
Okay, doctor. Clear, doctor.
Okay. Now we are going to study the formula for entropy. What is the formula for the entropy? My dear, could you please remember in chapter number 19, we have one problem based on this condition. The last problem. If your heat will be positive, the heat is given to the system. Am I right?
Yes.
If the heat is negative, heat energy is negative, the heat energy is taken from the system. Am I right?
Yes, yeah.
Yes.
So you have the formula for entropy, 2 cases, 2 different formulas you have. What are the first formula? These 2 are exactly same. These 2 are exactly same. Change in entropy, which is equal to amount of heat energy divided by the total, divided by the average temperature. Suppose if you have 2 temperature, you can take the average, put it here. And if you have the heat energy value, substitute here. Both are exactly the same. This formula and this formula, both are exactly the same. Clear?
Clear.
Yes.
Okay, now we have another formula for entropy from the first law of thermodynamics. What is your first law of thermodynamics? Heat energy, which is equal to change in internal energy minus work done. Am I right?
Yes.
Okay, now I'm going to write the equation like this. What is the formula for entropy, my dear? For example, if you, oh, sorry, this is plus. So change in heat energy. That means heat energy, which is equal to change in internal energy plus work done. Am I right?
Yes.
Yes.
Okay.
Yes.
Now, what is the formula for work done? We study the formula P delta V. Am I right?
Yes.
So small amount of work done, P dV. Am I right?
Yes.
Okay. What is the formula for internal energy? We studied NCV delta T. Am I right?
Yes.
Therefore, change in internal energy, which is equal to, am I right?
Yes, you are.
Yes.
So now in this place, for example, in this place, I am going to write my change in heat energy. That means the amount of heat energy, which is equal to work done plus internal energy. Clear? In this place, I am going to substitute this formula. Understand?
Yes.
In this place, I am going to substitute this formula. Clear?
Yes, doctor.
Okay, now you will get this equation. Now, what is the formula for ideal gas equation? PV, which is equal to nRT. Am I right? Am I right or
Yes.
not? Therefore, P,
Yeah.
which is equal to,
NRT over.
so I am going to take this, I am going to substitute here. Clear? So how
Yes.
your equation is become? Your equation becomes like this: dq, which is equal to nRT dV over V plus NCV dt. Am I right?
Yes.
Okay, now I'm going to divide this equation by T. So this equation, this term becomes dq over T. Am I right?
Yes, you are.
And here if you put T, this T and this T get cancelled, and finally you have this term. Am I right?
Yes.
And here when you divide by T, the equation becomes like this. Am I right?
Yes, you are.
So now you can integrate each and every term with the initial and the final value of the respective term. So here I am going to integrate with the initial temperature and final temperature, and here I am going to integrate with the initial volume and final volume, and here I am going to integrate with the initial temperature and final temperature. So my equation becomes like this. Am I right?
Yes.
And here if I take this NR outside, these terms become natural log of V final over V initial. Am I right?
Yes.
And this equation, when you take NCV outside, this becomes natural log of T final over T initial. Am I right?
Yes.
So if you substitute, if you consider your temperature is constant, this becomes initial temperature over final temperature over initial temperature have the constant value. Therefore, natural log of 1 becomes,
0.
so this term will gone. Am I right? If you have the constant temperature,
Yes.
when you put the final temperature and the initial temperature same value, what will happen? Natural log of 1 becomes 0. So this entire term will gone. Am I right?
Yes, but doctor.
Yes.
So you have only these two terms. And what is this, my dear? This is nothing but
That is.
delta S, which is nothing but change in entropy. Am I right? So my change in entropy, which is equal to, I can take this term outside. So by that, when you integrate, you will get this term. So the another formula for entropy is delta S, which is equal to N or natural log of final volume over initial volume. Clear?
Doctor,
Clear.
Yes.
why the last part it will be 0?
Because of the constant temperature. So this term, I can just explain this term here. You can listen here, my dear. If you take NCV outside, you will get dt over t. Am I right? This is
Yes.
initial value, final value. Am I right?
Yes.
So if you integrate this dt over t, you will get
will become length.
NCV natural log of TV over T, sorry, T final over T initial. Am I right?
Yes, you are.
If you have the isothermal condition, your initial temperature which is equal to final temperature. Am I right?
Okay. And it
So
will
this
be
term
1.
becomes NCV natural log of 1. Am I right?
And yes,
And
so
this natural log of 1 is 0. So all the terms will gone. Am I right?
yes.
That's what our last term of this equation disappeared. Clear?
Yes, clear. Thank you.
Okay. Now I will give you one example and which is given in this slide. My dear, I need your attention. Please just respond me if I ask you the question. Here I gave 2 pictures. Yes.
We have to know how we got this formula, or we have to know the final formula.
No. Just remember this formula. This formula is enough. These 2 formula is enough.
Okay.
Clear?
Okay.
Okay. Now you can see the picture. What we studied in the before slides. Our entropy of the system is always
More than 0 equals 0. Increase.
it's always has the positive value. Increase means it's always has the positive value. Am I right?
Yes, you are.
Okay, now you can see the picture. I have 2 different pictures. You can see here, I take one vessel full of water and I take another bowl full of water. And how much quantity of water I took?
250 grams.
250.
And what is the temperature of this water?
100.
100.
Okay, what is the temperature of this water?
0.
Okay, now I connected these 2 vessels with a conducting material. When I just put this conducting material which connects both vessels of water, what will happen?
It will be 50-50.
Heat will be transferred from hot region to the cold region. Am I right?
Yes, you are.
Yes.
So after sometimes what will happen?
It will be equal.
Both vessels have the same temperature. So for example, this have 50 degrees Celsius, this have 50 degrees Celsius. Am I right?
Yes, you are.
Yes.
So now I am going to apply the condition of this delta S for the system 1. And then I am going to apply the delta S for the system 2. Clear? And
Yes.
then I am going to find the entropy change in delta S for the entire system. Understand, my dear? Clear?
Yes, doctor.
Okay, now I need the answer from your side. What is the temperature here? It is 100. It is a 0 degree Celsius. And after what will happen? 50 degree, 50 degree. Am I right? That means this is my initial temperature. This is my final temperature. Am I right? Of the first system first. Am I right?
Yes.
And what happened to the second system? This is my initial temperature. This is my final temperature. Am I right?
Yes, you are.
Could you please apply the change in entropy for this case? What will happen? Change in entropy which is equal to delta Q over T average. Am I right?
Yes.
And we studied the formula for delta Q. What is the formula for delta Q? MC delta T. We studied this formula. Do you remember that?
Yes.
So I apply the formula here. So I can write the formula like this. Am I right or not?
Yes, you are.
Okay, now what is the mass of the water? What is the mass of the water?
250 grams.
250 grams. So I converted to kilogram. And what is the specific heat capacity of the water? This is the constant value. Clear?
Yes.
Yes.
Okay, and then change in temperature. Final temperature minus initial temperature. Which is your final temperature here? 50 is the final temperature. Am I right?
Yes.
What is your initial temperature?
100.
So you got the term like this and divided by average temperature. What is the temperature here? Here 100 and here 50. How you can find T average, my dear? 100
Added
plus
on
50 divided by 2. Am I right?
Yes.
You got some answer here. 75 degrees. 75 you got. Am I right?
Yes.
And if you convert it to Kelvin, you have to add 273 by this value. Am I right or not? Then you will get 348. Understand?
Yes.
So what is the entropy? Change in entropy of the first system? It has negative value. Am I right?
Yes.
Yes.
So the entropy of only one system here negative. Okay, let's we find the same entropy for the second system.
The
Again,
other
I am
will be
using the same.
positive.
Doctor,
Huh? What?
Will
What?
be positive, the second one.
My dear, the entropy of the full system will be positive. Here we are talking about only one system.
Yes, yes, I mean the second system will be positive.
Second system, when you are using the same case, you will get the positive value. Am I right?
Yes, and when
Doctor,
you
why
add
did
it
you
So
to
what
the
is the
use
two, will
entropy?
be
calculus?
double
What is the entropy of the whole system? So this
positive.
system plus this system, what is our final answer?
Must be positive.
Positive.
Must be positive. You should not get negative value. If you get negative here, you can just think by yourself, you made some mistake. Clear?
Yes.
Oh, clear.
Understand,
Yeah.
my dear?
Doctor,
Yes.
why didn't you use Kelvin in the initial temperature?
If you are
Yeah.
using the temperature, my dear, what is the unit here, my dear? We have to use SI unit. What is the SI unit of the temperature?
Okay, I got it.
So we have to convert the Celsius to Kelvin. Understand?
Yes.
Okay. Now, let's we come for our last slide of this chapter. What is the entropy in the real world about the engine? My dear, we already studied no 100% efficiency. Am I right? Am I right or not?
Yes.
Is it possible to get 100% efficiency of the engine?
No.
Okay, no, it's not possible. So there may be some loss of energy. Am I right? So here, if you want to find the efficiency of the engine, my dear, listen carefully. If you want to find the efficiency of the engine is indicated with a notation eta. So this is called as eta. You have to write like this. Clear? Clear? So if you want to find the efficiency, my dear, you can just see the picture. You take all the energy from the hot reservoir to perform this work. Am I right?
Yes.
So our ultimate aim, we have to get some work done. Am I right or not?
Yes.
So for getting this work done, where you take the energy? You take the energy from the hot reservoir. Am I right?
Yes.
So energy we get is work done, and energy we pay for getting this work done. Where we take the energy? We take the energy from the hot reservoir. Understand?
Yes.
What is your work done? Your work done is nothing but QH minus QC. Am I right?
Yes.
So that's what we write the term like this. Clear?
Yes.
Clear, doctor.
If you simplify this equation, you get this equation because QH divided by QH 1. Am I right?
Yes.
Minus QC over QH, you will get this equation. Am I right?
Yes.
So where we got this equation? My dear, actually, this equation is exactly coming from this Carnot engine. Actually, Carnot is the name of the scientist. You know what he did? He designed an ideal engine. What is the meaning for ideal engine? It's an imagination. Am I right?
Yes.
So this Carnot engine gives you 100% efficiency. But in the real world, 100% efficiency engine, it's not possible. Clear? Clear?
Clear.
So
Clear, yeah.
we took the formula from the Carnot engine here, but in your syllabus, this Carnot engine topic is not there. So don't worry, but we only take the final formula. Clear?
Okay.
Doctor,
Yes.
what's the difference between the efficiency in the first slide and the efficiency in this slide?
This slide, both are same. Both are same. Here efficiency. How you can write the efficiency, my dear? I can write the efficiency QH minus QC over QH. Am I right?
Yes.
So if you simplify this, this becomes. Am I right?
No, I mean in the first slide where it's
Which slide, my dear? I
PH
told you
minus-
this is an.
Oh, this one is the ideal efficiency. Oh.
Ideal. So in ideal cases, your cold temperature over hot temperature is exactly equal to the cold energy over hot energy. But in the real world, is it possible?
No.
No. Keep this information. Understand?
Yes, I got you. Thank you.
If both are equal, then it is a case for ideal cases, but in the real world, it is not possible. But we can use that formula. Even if you want to explain the concept of the real engine, we have to give the honor to the Carnot. That's what we are taking the formula from the Carnot engine. Clear?
Yes, it's clear. Thank you.
So you can read the question. If the question has the information about the hot reservoir, cold reservoir energy, then you have to use this formula. Suppose if the question related with the Carnot engine have only temperature, about high temperature and low temperature, you have to use this formula. Both are exactly the same. You can see here, I replace this QC with TC. I can replace this QH with TH, which is equal to my efficiency. Clear?
Yes, clear, Doctor.
Okay. Now, let's come for our refrigerator. My dear, this is the reverse diagram of the heat engine. Just before I told you, we are talking about the refrigerator or air conditioner. So what is our ultimate aim? Our ultimate aim to make our room cold. Am I right? Am I right or not?
Yes, yes.
So
Yes.
what we need? We need the cold energy. Am I right or not? And for getting this cold energy, what you have to do? What you have to do? You have to do some work. Am I right?
Yes.
Am I right or not?
Yes, because we
Yes.
are doing the reserve thing.
My dear, if you, our ultimate aim of the refrigerator and the air conditioner, we have to make the room, or we have to make the refrigerator colder inside. Am I right? You can just do one thing, my dear. Open the refrigerator. What temperature you observed inside the refrigerator?
Colder temperature.
Colder. Okay. Go back to the refrigerator. What temperature you observed? Did you see the backside of the refrigerator? Did you see the backside of the refrigerator?
Yes, it's hot because it takes.
It's hot, and you can see there is a compressor. So what is exactly doing there? It will take the heat energy from inside and it will be throw that heat energy outside. Am I right?
Yes.
That's what inside the refrigerator you feel colder. Outside, that means backside of the refrigerator, you feel hotter. Clear?
Yes.
Victor, can you repeat it, please?
If you take the refrigerator, this is the refrigerator. Okay.
Okay.
Backside of the refrigerator, did you see this type of coil?
Yes.
So inside, if you put one apple, for example, if you put any material, for example, this material hot, and you put this material inside the refrigerator, what happened, my dear? You can see there is a tray. Am I right? So all this tray, the gas is moving. So when you place any hot material inside the refrigerator, what happened? This heat energy will be taken away, and then this heat energy will be thrown outside. It will be taken inside and it will be thrown outside. So what you observe inside the refrigerator, what temperature you have?
Cold.
What temperature you have here?
Hot.
Okay, if you see the back side, you see some black color material. Am I right or not?
Yes, you are.
Some cylindrical shape. What is that?
Ball.
Gas.
What is this?
Compressor.
This compressor is doing this work. This compressor is pushing some gas inside, and that gas will be take this heat energy and it will be throw that heat energy outside. So without compressor, is it possible to run the refrigerator and AC?
No.
So what you observe here, we need cold temperature. So the coefficient of performance of the refrigerator or AC, which is equal to, we need cold temperature, and for getting this cold temperature, what we have to do? We have to do some
Work done.
work with the help of
Compressor.
So if you just simplify this equation, QC I can write, and what is my work done? H minus QC. Am I right? So heat energy hot minus heat energy cold. Am I right?
Yes, you are.
If you want to rewrite this equation in terms of temperature, how you can write? You can write TC over Th minus Tc. Clear?
Yes.
Clear, my dear?
Yes, doctor.
That's it. So these two formulas are very, very important, my dear. So you have either the question from this chapter is related with the Carnot engine or Carnot refrigerator. If it is Carnot engine, write the formula. If it is a Carnot refrigerator, write this formula. Clear?
Yes.
Yes.
Okay, that's it. Chapter is over and we are going to solve this problem. Clear? I think so right now the time is exactly 1:06. Am I right? Still we have 40 minutes. Am I right? 40 or
Yes.
35 minutes. Am I right?
Yes, we can solve all of it.
Yes, we can. I have to finish today. So before that, could you please recall the formula, my dear? Could you please recall the formula? What is the formula for change in entropy? The formula for change in entropy is
Q.
dq over T or delta Q over T average. Am I right? Am I right?
Yes, you're right.
And another formula for change in entropy, N or natural log of V final over V initial. Am I right?
Yes.
And then what is the formula for efficiency of the engine? Eta, which is equal to work done divided by QH. Am I right? And work done, which is nothing but QH minus QC over QH. If you want to simplify this, you can write this term as QC over QH. Am I right? If you want to write the same equation in terms of temperature, how you can write? Work done, which is equal to work done divided by TH. So if you simplify this, TH minus TC over TH. Am I right? Which is equal to 1 minus TC over TH. Clear?
Clear, yes.
And what is the formula for a refrigerator? The coefficient of performance, which is equal to QC over work done. And what is our work done? Our work done, which is nothing but QH minus QC. Am I right? In terms of temperature, the same formula, I have to replace this Q with T. Clear?
Yes.
Yes, sir.
That's it. So this formula we are going to use in the formula in the question. So these five questions we are going to discuss now. Clear? Okay, my dear, I need the answer from your side. This is the first question. Could you please tell me whether this question is related with engine or refrigerator?
Engine.
Engine, am I right? Okay, now what is the formula for engine? First of all, please write the formula. What's the formula? Eta, oh sorry, I can click this. What is the formula? Eta, which is equal to, because the question is given in terms of
One.
temperature, am I right?
Yes, 1 minus.
So the question is given in terms of temperature. So I have to write the equation in terms of temperature. So what is the formula for temperature, my dear? TH minus TC divided
over
by
TH.
TH. Clear. That's it. Now, let's just read the question. What is given here? The Carnot engine has the efficiency. So the efficiency is given. That means eta value is given. Am I right?
Yes.
So if it is 15%, what you have to do? 15 divided by 100 gives you
0.15.
0.15. Okay, let's continue. What is given here? And this engine is operate between constant temperature reservoir differing in temperature by 55 Celsius degree. What is the Celsius degree?
The delta.
That means change in temperature. So what is our change in temperature, my dear? Delta T is given. That means TH minus TL value is given as
55.
Okay, now what you are going to find? We are going to find the value of
Lower temperature.
lower temperature we are going to find. My dear, listen carefully. They give the efficiency, they give the change in temperature, but we have to find the value of the lower temperature. But if you want to find the answer in terms of lower temperature, my dear, either you can write TL or TC, both are correct. Understand? Low temperature, cold temperature, both are correct. Understand?
Dr.
Yes.
TL is mean TC.
My dear, what is the formula? Here TC I can write. If you want to write in terms of TL, both are correct. Clear?
I mean the lower temperature is TC.
Okay, I can come to your point. Better I can write the formula in terms of C. That will be quite a good. Okay, forget about that. I think you will get confused if I just write a TL. Okay, I can just delete this. Okay, and also I can delete this. What we are going to find now? Now you can tell what we are going to find. Clear?
Yes.
So if you want to find the value of this cold temperature, that means low temperature, you need the information about high temperature. Am I right?
Yes.
So first, what you have to do, without help of this high temperature, you never get the value of this low temperature. So first, we have to find what is our high temperature. So I am going to use this equation, and what I am going to do from this equation, I am going to find the value of this TH. My dear, I can write this formula as eta, which is equal to delta T over TH. Am I right? Shall I write like this?
Yes.
You can write.
We can write. Am I right?
And rearrange this equation.
And rearrange this equation. Therefore, TH, which is equal to delta T over eta. Am I right?
Yes, you are.
And you have the value of this delta T. What is the value?
55.
55,
55
yeah.
Celsius degree. My dear, listen carefully. Celsius degree is exactly equal to
The Kelvin degree.
Kelvin. So don't worry about the Celsius degree. If you want to write Kelvin, no issue. That is also correct. Either you can write 55 Celsius degree or 55
Kelvin.
Kelvin. Both are correct. Understand?
Yes.
Okay. Divide by eta. What is the value of eta?
0.15.
So you will get the answer for TH. Am I right?
Yes.
The unit is Kelvin. Am I right?
Yes.
Yes.
Okay. Now we got the value of this TH. Now what we have to find? We have to find the value of
TC.
Okay, now again I can write the same formula for the efficiency. What is the formula for efficiency? TH minus TC divided by TH. Am I right?
Yes.
I can move this here. Then my equation becomes eta TH, which is equal to TH minus TL TC. Am I right?
Yes.
So we have to find, so I am going to move this term to the left hand side. I am going to bring this term to the right hand side. So I will get TC, which is equal to TH minus of eta multiplied by TH. Am I right?
Yes, you are.
Take the value,
TH.
substitute here. Eta value is already given in the question. You will get the answer of this cold temperature in terms of Kelvin. Understand?
Yes, Doctor.
Ah.
Celsius degree is equal to Kelvin, but degree Celsius is not equal to Kelvin.
Yes, my dear. Actually, in the slides, I put degree Celsius. But please, it's my kind request to all of you. It's my kind request to all of you. Please change this degree Celsius in terms of Celsius degree. Clear?
Yes.
In the slide, it is not a degree Celsius. This is Celsius degree or
Kelvin.
Kelvin. Better you can write Kelvin. That will be quite enough. Understand?
Doctor,
Yes.
degree Celsius is not equal to Kelvin.
Yes, degree Celsius is not equal to Kelvin. My dear, listen carefully. Degree Celsius is not equal to Kelvin, but Celsius degree is always equal to
Kelvin, yes.
Okay, keep this point. Understand?
Yes, Doctor.
Okay. Is it clear?
Doctor,
Is there
I
any
have a
doubt
question,
here?
please.
Yes.
Yes.
Doctor, we find the TH, right?
Yes.
Can I say TC equal delta T minus TH?
What is that? Tc is equal to
delta T minus TH.
Tc, which is equal to delta T minus
TH.
eta
TH. Minus TH.
minus Th. How you got? Is it correct?
I asked you, can I say
Yeah,
like
of
this?
course. Yes, no problem. This is also correct.
Okay.
You can
Because
use this also.
he
I
give
think it's a correct.
yes, yes.
Clear.
Clear, doctor.
Okay,
Clear.
very good. Okay, shall I go to the second question? Okay, tell me whether this question is related with the engine or a refrigerator.
Engine.
Engine.
Okay, so
Engine.
the engine question, but what they give the information about the energy. Am I right?
Yes.
Kilojoule.
So what is our first temperature? So the Carnot engine absorb 52 kilojoules. So that means it will take hot energy. Am I right? It is taking hot energy. How much?
Minus 3.
Clear.
52.
And it exhausts 30 kilojoules as heat in each cycle. That means it's throw this much of heat energy to the cold reservoir. That means QC, which is equal to 30. Am I right? 10 to the power of 3 joules. Am I right?
Yes.
Yes.
Yes, doctor.
What you are going to find? You are going to find what is the engine's efficiency. That means we are going to find the value of eta. And second question, we are going to find what is the work done. Am I right?
Yes.
Yes.
Okay, let's write the first question answer. We know the formula. What is the formula? Eta, which is equal to
1 minus KC over KH.
TH minus TL or TC. No problem. You can write 1 minus. That is also correct. Okay. But I can just write like this. TH minus TC over
Yo,
TH. Am I
doctor.
right?
QH.
Oh, sorry. QH. QH over QC over QH. Am I right?
Yes.
Yes.
Okay. Now we have to find the value of eta. Am I right? So, my dear, substitute the value. What is the value of QH? 52 multiplied by 10 to the power of 3 minus
Yes.
30 multiplied by 10 to the power of 3 divided by 52 multiplied by 10 to the power of 3. You will get some answer. Am I right?
Yes, and the
I think when
unit.
you work out, you will get the answer of 0.423. Am I right?
Yes.
Yes.
What
Yes.
about the unit?
But
is
we
Joule.
have to give the answer in terms of percentage because eta, it should be in the percentage. So what you have to do? You have to multiply by
Multiply by 100.
100?
100. So what is the answer? This is the answer for the
42.3.
eta. Clear?
Yes.
Okay,
Clear.
now let's come for the second question. What is our second question? Work done.
Work
What is the
done.
formula for work done, my dear? QH minus QC. Am I right?
Yes,
22.
you are.
Yes.
So direct question. What is QH? 52 multiplied by 10 to the power of 3 minus 30 multiplied by 10 to the power of 3. So 52 minus 30, exactly 22 multiplied by 10 to the power of 3. Unit is joule, and this will be the answer for the second question. Clear?
Doctor, he wanted
yes.
by kilojoule. Kilojoule.
No problem. If you want to write like this, no issue. No issue. That is also correct.
Okay.
Clear?
Clear.
Yes.
Okay. I can just move to the third question. My dear, I can just solve this third question at the last, okay? Because it's a little bit lengthy. First of all, we will finish all the easiest one. Understand?
Okay. Yes.
Okay. Just read the fourth question. What is given in the fourth question? This question is also related with engine. Am I right?
Yes.
So the
Yes.
Carnot engine operates between 235 degrees Celsius and 115 degrees Celsius. That means the high temperature value is 235 degrees
200.
Celsius. Am I right?
Yes.
Yes.
The low temperature value is 150. Am I right? And while it takes this energy, how much of energy it absorbs from the hot reservoir? It absorbs this much of energy. Am I right? Am I right or not?
Yes.
You can see they clearly mention. What is this?
Higher temperature.
That means the energy from the higher temperature is nothing but QH. Am I right?
Yes.
Okay, what you are going to find? You are going to find two questions. The answer for the two questions. What you are going to find in the first question? How much energy per cycle is discharged at the lower temperature? That means you are going to find the value of
QL or
QC.
QC.
QC or QL, both are correct. And what is your second question?
The work.
Work done. Clear? Okay, now again, could you please recall the formula? This question is related with the engine. So what is the formula, my dear? Eta, which is equal to TH minus TC over TH. Am I right?
Yes. Yes.
Yes.
Am I right? So now, if you want to find the answer for this low energy, that means the energy from the lower temperature reservoir, you need the information about the eta. Am I right?
Yes, sure.
So with the
Yes.
help of the temperature, first I am going to find the eta, and after that I am going to use this eta here to find the answer for the low temperature. So the energy in the low temperature. Clear?
Yes.
Okay. Could you please substitute the value? What is your high temperature? 235 and low temperature 115 divided by TH. What is your TH, my dear?
235.
235.
235, but you have to convert it to Kelvin. Am I right?
Doctor, why the above one? You didn't convert it.
My dear, even if you convert, you will get the same answer. Just before I told you, Celsius degree, which is equal to Kelvin. This is the
That's
change in
mean that-
temperature, am I right? This is change in
Yes, it's
temperature, am I right?
delta T. Yes.
So why you are wasting your time by adding 273? You will get the same
No.
answer.
Yes, clear.
Even if you want to add 273, no problem. Your answer is correct. But why you are wasting your time? Clear?
Yes, doctor.
Clear, doctor.
Or else, my dear, I can come to your point. If you
Teacher,
want
I
to
don't
write,
understand
no problem.
this thing.
What?
I don't understand why didn't you convert it the denominator?
Okay, listen. What is your higher temperature, my dear? Could you please tell me the higher temperature?
235.
235. If you add 273, what is the answer? 8, and this becomes 0. This becomes 5. Am I right?
Yes.
Okay. What is your low temperature? If you add 273, what you will get?
8.
You will get this. Am I right?
Yes.
Okay. What is the answer for TH minus TC? 508 minus 388. What is the answer, my dear?
150.
I got 120. Am I right? Am I right?
Yes.
Okay. Without converting, could you please find the answer? What is the answer for this? 235 minus 115. What is the answer, my dear?
120.
Why you are wasting the time by adding this here? Because when you find the change in temperature, the answer remains the same. But in the bottom, my dear, listen carefully. But in the bottom, you have only one temperature. It is not a difference. It is only one temperature. That's what we have to add 273 here.
Yes.
Doctor,
Yes.
you mean the delta T, the answer for it, Celsius degree.
So that's what I write it here already.
Yes.
Clear. But here you have only one temperature. That's what I add 273. If you want to convert to Kelvin, no problem, my dear. Go in your own way. But don't waste your time. Clear? Clear?
Yes, doctor, clear.
Yes.
Okay. Now, when you substitute the value, you will get the answer of eta. Am I right? You get some answer. Am I right?
Yes.
Am I right or not? And now, once you got the eta, with the help of this eta, first we have to find what is our QC. Am I right? Okay, my dear, could you please solve and tell me the answer? Could you please solve and tell me the answer? 235 minus 115 divided by 235 plus 273. I got 0.236. 0.236. 236 I got. Am I right? Am I right or not?
I got 0.51.
Solve carefully, my dear. How you got 0.51?
Okay, maybe I'm mistaken.
Check. I got exactly 0.236.
Yes, yeah.
Okay, now, could you please tell me the formula for eta, my dear? We can write the eta formula in terms of energy. I can write like this, am I right?
Yes.
Am I right? Okay, now what I am going to do, I am going to keep this term here. I am going to take to the left hand side and I am going to bring this eta to the right hand side. So how your equation becomes? Your equation becomes QC over QH, because this negative, when it comes to the left hand side, it becomes positive. Am I right? And when this
Yes.
eta comes to the right hand side, it becomes
One
negative.
minus.
Am I right?
Yes.
Okay, now after I just move this, I'm going to bring this QH to the right hand side. So how you will get QC, which is equal to QH multiplied by 1 minus eta. Am I right?
Yes.
Okay, now what is the value of QH? It is already given in the question. What is the value of QH? What is your value of QH, my dear?
3 multiply 10 power 4.
So 3 multiplied by 10 to the power of 4, 1 minus eta value 0.236. So when you just work out, I got, I think 7.08 I got. So sorry, I got, that is for the work done. What is the formula for work done? Better we can write the formula. What is the formula for work done, my dear?
QH minus QC.
QH minus QC. Okay. So here when I just work out 3 multiplied by 10 to the power of 4 multiplied by 1 minus eta 0.236, I got 22,920. So I can write these as 2.2 multiplied by 10 to the power of 4. Am I right?
Yes.
Am I right?
Yes.
Okay, now for the second question, this is the answer for first question. For finding the second question, I can just write this formula. What is my QH? My QH is 3 multiplied by 10 to the power of 4. Am I right?
Yes.
Yes.
Is it correct? 22920. So 2 point, okay. 3 multiplied by 10 to the power of 4 multiplied by 1 minus eta 0.236. I will check again. 22920 joules. Clear?
Yes.
Okay, minus 2 point. What is your QC? Is it possible to use this formula here?
Yes.
What is the answer?
0.8 multiplied by 10 power 4.
No. I think 0.8 is not possible. Okay, better I can use this formula. Eta, which is equal to work done divided by QH. I can write like this. Am I right?
Yes. Work equal
So
to
therefore work
multiply.
done, which is equal to eta multiplied by QH. Am I right?
Yes.
What is my eta? 0.236. What is my QH? 3 multiplied by 10 to the power of 4. When you just work out 0.236 multiplied by 3 10 to the power of 4, I got 7.1 kilojoules. Am I right?
Yes.
Am I right?
Yes, doctor.
Clear? Clear, my
Clear.
dear? Yes.
Why, teacher, why didn't you
No,
work with
doctor. Oh, 7.1.
How?
Yeah. It's showing in the calculator 7,080.
For this or this?
No, for 0.236.
My dear. What's the
No,
value?
okay,
7080. Am I right?
Joules.
I can write these as a 7.08 kilojoules, 10 to the power of 3 joules. Am I right? I can just round it this value 7.1 multiple kilojoules. I can write like this. Am I right?
I changed the kilojoules.
If you want, you can write. Otherwise, you can leave here as it is.
Okay, teacher. Why don't we use the previous equation? The answer.
What is our value, Okay, what is our value? Let's check. I think you can use this. I think so. Because work done which is equal to just a minute. Work done which is equal to QH minus QC. Am I right? What is your QH?
Three times 10 4.
My dear, listen carefully. 3 multiplied by 10 to the power of 4. Am I right? Minus $22,000. I can write like this. So 3 10 to the power of 4. Okay, my dear, listen, my dear. Why I am not using this? Then what is the purpose of finding the eta value? Because when you are finding the value of work done, you must add the efficiency. Am I right?
Oh, yeah.
Do you get my point?
Yes.
This is the general formula for the work done, my dear. But when you are finding the work done for this reaction, you must add this eta. This is very, very important. Am I right? Am I right or not?
Yes.
My dear, when you are finding the work done, the efficiency you have to add. Without adding the efficiency, how you can use this QH minus QC? Is it possible? Is it possible? It's not possible because you have to use the efficiency here. Without using this efficiency, how you can find the work done? Because this efficiency is a part of the calculation. Am I right?
Doctor, in the previous example, you solved, I think, like that.
Which one?
I don't know exactly.
Where you are talking, my dear? I don't understand what you are saying. Where you are talking?
In the previous example.
In the previous example of this type of question?
I think you solved like that.
Okay, let's see where we solve.
Part B.
You are talking about this?
Yes, doctor.
Okay, let's see here.
What's the difference between them?
This is a QH minus QC. We can directly substitute the value, but here we are just finding the. You can see here, my dear. You can see. Is there any information about the temperature we are using here?
I know.
No.
Because here the question is purely we are substituting the energy only. Am I right?
Yes.
Okay, you can see this question. This question has the information about the temperature as well as the energy. Both information is there. So when you are using these both cases, you must add the eta, the efficiency. So here we should not use this QH minus QL. Why you can't use this temperature? TH minus TC also you can use. Am I right?
Yes.
Yes.
Why you are not using that? Why you are not using? Because here you have temperature, high temperature and low temperature. Why you are not using W which is equal? Why you are not using W which is equal to TH minus TL?
Because it's energy.
Because this question they give the temperature as well as the energy. So eta you have to include here. Without using this eta, how you can use this? Because it's not possible. Understand, my dear?
Okay, doctor.
In this question, only energy information. There is no information about the temperature. That's what we are using. W which is equal to QH minus QZ. When you come to this question, temperature also given, energy is also given. So in such a case, you should not use this formula. You should not use this formula. You have to use, because we have to apply the value of this eta. Understand?
Yes, teacher.
Yes,
Because if I come to your point, why you are not using the temperature, my dear? Is it possible to use this? Because this formula is also correct, am I right?
Yes.
Am I right or not? So why you are not using this? Because if you are using this, we have to add this eta. Eta is very, very important. What is the purpose of finding the eta here?
Doctor, in the previous example, if I use this formula, the value over QH, it will give me the same answer.
Like this?
Yes.
Yes, you will get the same answer, because all the informations are related with the energy. You will get the same answer. My work done, which is equal to eta multiplied by QH. Work out the answer. You will get the answer for sure.
So if you give me the temperature, I can solve it by 2 ways.
Yes, my dear, if the question have only the temperature or only the energy, you can go for this formula. But if the question have both the temperature as well as the energy, you should be very, very careful. Clear?
Okay. Thank you, Doctor.
Let's come for the last question here. So what is given here? What is given here, my dear? Read the question. Suppose 2.0 moles of an ideal gas undergo the reversible isothermal reaction. My dear, listen carefully the word. What is given here?
Isothermal.
Isothermal. What is the meaning for isothermal, my dear? If the reaction is isothermal, what is your change in internal energy? It's zero, am I right? And during this reaction, what is your volume? My initial volume is V1, and what is my final volume? 0.5 times of V1. That means my number of moles is given, 2 mole. And what is my initial volume? My initial volume is V1, and what is my final volume? 0.5 times of V1. Am I right? Am I right?
Teacher,
Yes.
the initial is V1.
That means it says 1 V1. My volume from V1 means it's 1 V1. Am I right?
yes.
So my initial volume is 1 times of V1. My final volume is 0.5 times of V1. Clear?
Work will be zero, Doctor.
What?
Work will be zero because land.
My dear, if it is an isothermal condition, your change in internal energy only is equal to 0. Your work is not equal to 0. Your change in internal energy is equal to 0.
Because then final V final equal V initial.
My dear, isothermal, your temperature is constant, my dear. Don't confuse everything together.
Clear now, Doctor.
Don't get confused about the temperature and the volume. Here temperature is constant. Your change in internal energy is equal to 0. So these informations are given. What is your temperature? Your constant temperature is given. What is the value? 400. Am I right? Now, what are the things you are going to find? First, we have to find the work done. My dear, chapter number 19, we studied for isothermal work done, which is equal to nRT natural log of V final over V initial. We studied this formula. Do you remember that?
Yes, Doctor. Yes.
So I can directly use this equation here. Am I right?
Yes.
Am I right? What is the value of N? It is given. What is the value of R? It is 8.314. What is the value of T? 400. So when you substitute, you will get the answer. Am I right?
How about V initial and V final?
What is V final? What is V final?
0.5.
My dear, I thought you are genius guys, but you need the steps, huh? Okay, no problem. I can try. So 2, number of moles. What is your R value? 8.314. Am I right?
Yes.
Am I right?
Yes.
Yeah.
Okay, what is your temperature? 400. Am I right?
400. Yes.
Okay,
Yes.
what is your natural log? What is your V final? 0.5 times of V1. Am I right?
Yes.
What is your V initial? It is 1 V1. Am I right?
Yes.
This V1 and V1 get cancelled. Am I right?
Okay.
So 2 multiplied by 8.314 multiplied by 400 multiplied by natural log of.
0.5.
So you will get some answer here. Am I right or not? Clear?
Yes.
This is the answer for the first question. What is your second question?
The entropy.
They need the change in entropy. My dear, what is the formula for change in entropy, my dear? Change in entropy, which is equal to Q divided by T average. Am I right? Am I right or not?
Yes, you are right.
Yes.
Okay, now, is there any information about Q here? Is there any information about Q here?
No.
Okay, but they give the information about isothermal. Am I right?
Yes.
What is the
Yes.
isothermal?
Work
I
equal.
told you
equal
change in
work.
intelligence is equal to 0. So I'm going to write the first law of thermodynamics. What is your first law of thermodynamics? Q, which is equal to change in internal energy plus work
Yes.
done. Am I right?
Yes.
So your change in energy is 0 because of the isothermal condition. Am I right?
Yes.
So Q, which is equal to.
Work.
So in this place, I can put W here. Am I right?
Yes.
So I can take the answer of the first question. I can substitute here, divide by what is my temperature. This is the normal temperature, average temperature. Divide by 400. You will get the answer. Am I right?
Yes.
Clear?
Teacher, the answer for the W I got minus 4,610.
So you got the answer in terms of minus. Am I right? So
Yes.
here also you will get the answer of change in entropy negative. Am I right?
Mhm.
Okay, my dear, this is not a system because they never mentioned the entropy of the whole system. Maybe entropy of one system is negative, but when you just go for finding the entropy of the whole system, what should be the answer?
Positive.
Positive. Clear? Because they
Oh.
clearly mention what is the entropy change of only the gas. They are not mentioning the entire system. They are just only mention the gas.
So we just like the normal answer, but positive. The same. We
Yes,
just
you can write the negative answer as it is because this information is related with the entropy of only one system. My dear, the entropy of one system, no problem. You can get negative, but the entropy of the whole system always positive. Keep this point in your mind. Okay.
Okay.
Okay. Now, could you please tell me the answer for the last question? If the compression is reversible and adiabatic instead of isothermal, for example, this question is related with isothermal. Suppose instead of isothermal, if you have the reversible adiabatic, what should be your entropy? My dear, we studied two cases. Am I right? If it is a reversible reaction, what should be your entropy?
Equal
If
0.
it is irreversible,
More than 0.
greater than 0. So out of these two answers, you can read the question whether the question is related with the reversible or irreversible. What is given here?
Reversible.
So if it is reversible, what is your entropy, my dear? This or this? Just tell me the answer.
Constant.
This will be the answer. Clear?
Yes.
Clear?
Clear, doctor.
Okay, my dear, listen carefully. Tomorrow we have one period. Inshallah, in that period, I will solve this question and then I will start chapter number 21. Listen, my dear, for your midterm portion, we consider 6 chapters. How many chapters?
6.
6 chapters, starting from 16 to 21. So, chapter number 16, 17, 18, 19, 20, 21. Totally 6 chapters. My dear, still we don't know about the type of exam, whether it is in the campus or in the online. We don't know. But anyhow, be prepared for both. Clear?
Okay, doctor.
Clear, my dear?
Could you please repeat? Because
For your midterm exam, we consider 6 chapters. That is nothing but from chapter number 16 to chapter 21. Clear?
Clear.
Okay. We don't know about the type of exam because we are going to whether we are going to write the midterm exam in the campus or in the online. We don't know. Clear?
In week what, Doctor? 7 or 8?
Week number 8. Generally, the midterm exam in week number 8. My dear, listen carefully. We don't know about the type of your midterm exam. So for both cases, either if it is in the campus, be prepared for that. If the exam is in the online, be prepared for that. Okay, but we don't know still now. Still now, I have no idea about whether what type of exam we are going to conduct. Maybe by this weekend or next week, we will get the information. Clear?
Clear.
Yes, clear, doctor.
So
You still have no idea about the formula sheet?
My dear, no formula sheet.
Okay.
No formula sheet. So you have to memorize all the formulas by yourself. Clear?
Okay, Doctor.
Yes,
Clear?
yes, doctor. Thank you.
Okay,
what
my
about,
dear.
Doctor, the numbers? Speed of air, speed or heat?
All constant value will be given in the question. So don't worry about the constant. The speed of the sound in air, the value of the R constant. That means the gas constant. What is the formula? What is the value for the Boltzmann constant? What should be the value for the molar mass? What should be the formula for the alpha? That means the thermal expansion coefficient. All this information will be given. Clear?
Okay, clear. Thank you.
But regarding the formula, you have to memorize. So far, no information about giving the formula sheet. So you have to memorize the formula from chapter number 16 to 21. Chapter number 21 is nothing. You are going to study I think two formula only. Only two formula in chapter number 21. My dear, listen carefully. In your exam, if you got any question from chapter number 20 and 21, please, it's my kind request, don't leave any question from this chapter. Because chapter number 21, you are going to study only two formula. In chapter number 20, we did only three formula. Am I right?
Yes, Doctor.
So please read the question and based on that, give the answer. It's my kind advice for each and everyone in this section. So inshallah, by next week or by this week, if I got any information about your midterm type, I will let you know through WhatsApp group or through the announcement. Clear?
Thank you so much, Doctor.
Clear.
Okay, my dear. Inshallah, tomorrow we have one period, 8th period, and by that class, in that class, I will teach this 39th question, and then I will move to chapter number 21. Clear?
Doctor,
Yes.
I have a question about the lab.
Okay.
My grade is not on Blackboard.
If your grade was not there, inshallah, you have to ask this question during the lab time. Okay, I will come with that sheet, then I will tell you.
Okay, thank you.
Okay, excuse me, my dear, I have one question. Please kindly respond me. Okay, I think I put this 1 hour. The period number 8 is the office hour. Am I right?
Yes.
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 Shall I finish this question now?
Okay.
Huh? Better we can start chapter 21 freshly. That will be quite good.
But teacher, I have
okay.
What, my dear?
I have another
I have
class.
something to do.
How many of
Yeah.
you have the class? How many of you have the class?
Me.
Me too.
My dear, 44 students you are here.
But Doctor, some of them left the class already.
Okay, forget about that. Okay, forget about that. No problem.
Thank
Okay,
you, Doctor.
inshallah, we will discuss tomorrow. If you are not showing interest, then why I have to give interest for that? Okay, no issue. Okay, my dear. Thank you so much. See you tomorrow.
Thank you, Doctor.
See you tomorrow. Assalamu alaikum.
Welcome salam.